All right, welcome. Today we're going to do something a little different. We're going to look up, way up, at those power lines that crisscross our world. We're going to dive into one of the most critical, yet, totally overlooked pieces of engineering that makes our entire electrical grid even possible, the insulators. I guarantee you've seen them. These ceramic or glass things that look like, stacks of plates or spools or little posts. They are not just decorations, not at all. They are busy solving a massive high-voltage problem 24/7. So what exactly are they doing up there?
Okay, so here's the basic problem, right? The metal wires carrying all that electricity, they're bare, they're totally uninsulated, and they have to be held up by towers, which are usually made of metal or wood, both of which can conduct electricity, and are stuck right in the ground. If you didn't have something in between, all that power would just zap right down the tower and into the earth. You'd have a spectacular and very, very bad short circuit.
And that's where our hero component comes in, an electrical insulator. It's made from a material, usually porcelain or glass, where the electricity just can't flow easily. It really has two crucial jobs. First, it has to physically hold up that heavy conductor wire. And second, it has to create a barrier, stopping that electricity from taking a shortcut to the ground. Simple, right? But incredibly important. So let's start close to home. We'll look at the insulators you're most likely to see right in your own neighborhood, on those local distribution lines that bring power down your street. Okay, so meet the pin insulator. This is one of the original designs, a real old-school workhorse. You'll see it on lines carrying up to about 33,000 volts. And the name says it all, really. It's mounted on a pin that holds it onto the crossarm of the utility pole. And the wire just sits neatly in a groove right on top.
And this is where the design gets really, really clever. You see those umbrella-like layers? They're actually called petticoats or rain sheds. Now think about it. When it rains, water coats the outside, and water can conduct electricity. But these sheds are shaped specifically to keep the surfaces underneath them dry. What this does is it makes the path for any leaking electricity incredibly long and broken up, effectively stopping it cold, even in a downpour. It's just brilliant.
Now, you might also see something that looks kind of like a pin insulator, but taller, maybe a bit beefier. That's going to be a post insulator. So what's the difference? Well, post insulators, as you can see, are built for higher voltages. They can even be stacked to get more insulation. And unlike a pin insulator, you can mount them horizontally. They also use a much more secure clamp to hold the wire instead of just tying it on top.
And one last one for our neighborhood field guide, the shackle insulator. Some people call it a spool insulator because, well, it looks like a spool of thread. You'll almost always find these on very low voltage lines, like the service drop that runs from the pole right to your house. Simple, cheap, and gets the job done.
Okay, so that's our local streets covered. But what about those huge transmission towers? You know, the steel giants that march across the countryside carrying electricity for hundreds of miles. Now we're talking about a whole different level of power, and that needs a whole different kind of solution.
The trusty pin insulator is great, but it has its limits. So what do you do when you're dealing with not just thousands, but hundreds of thousands of volts?
Well, if you tried to make a pin insulator for those super high voltages, it would have to be enormous. Just impractically big and heavy, and way too expensive to make. Engineers needed a better way, a smarter, more elegant solution that could scale up.
And this was the answer, the suspension insulator. Instead of one giant solid block of porcelain, engineers came up with a flexible string made of individual interconnected discs. The live wire then just hangs from the very bottom of this string.
And here's the magic number. Each one of those individual discs you see in the string is typically designed to handle about 11,000 volts of electricity. And this is what makes the design so absolutely brilliant. Need to insulate a 66,000 volt line? No problem. You just link 6 of those 11,000 volt discs together in a chain. Working on a much bigger line? Just add more discs. It's basically Legos for the power grid, a perfectly modular, perfectly scalable system. So why is this design so great? Well, for a few huge reasons. First, like we just said, it's scalable for any voltage you can imagine. Second, if one disc gets damaged, say by a lightning strike or a stray bullet, you don't have to replace the entire thing. You just swap out that one broken disc. It's also flexible, so it can swing in the wind, which actually reduces the physical stress on the tower itself. And as a neat little bonus, having the wire hang below the tower arm gives it a little extra protection from lightning.
But hold on, we're not done yet. There's another major challenge these insulators have to solve, and this one isn't just about electricity. It's about pure, raw, physical force.
So just imagine a transmission line that needs to make a sharp turn. or one that just stops at a dead end or a substation. That wire is pulling with an incredible amount of force, a huge tensile load. A normal, freely hanging suspension insulator just isn't designed to handle that kind of sideways pull.
And for this job, engineers use what's called a strain insulator. And here's the really cool part. It's the exact same technology. It's still a string of those suspension discs, but instead of hanging vertically, it's used horizontally to pull against that tension. It's designed to withstand incredible mechanical strain while also doing its main job of insulating the wire.
And this chart really shows you the extra stress they're under. For a 132,000-volt line, a normal vertical suspension string might need, say, 8 discs. But for a strain insulator on that very same line, you'll see they use 9. Why the extra disc? It's like a safety factor, to handle the combined load of both the high voltage and that much higher mechanical stress.
All right, you've got the theory down, so let's put it all together. We're going to build a quick field guide so you can become an expert insulator spotter next time you're out and about. So when you look up, here's what to look for. See those upright posts sitting on top of the cross arms of local wooden poles? That's your pin or post insulator. What about those long vertical strings of discs hanging down from the big metal transmission towers? Classic suspension insulator. If you see a similar string, but it's positioned horizontally, pulling the line at a corner or a dead end, that's a strain insulator. And finally, those little spools you see on the low-voltage lines, especially the one coming to your house, that's the shackle insulator.
You see, it all comes down to this simple idea. Each type of insulator, from that tiny shackle to that long suspension string, is a very specific tool designed to solve a very specific set of electrical and mechanical problems. It's just a perfect example of elegant, practical engineering.
They're pretty amazing, right? Hiding in plain sight, these silent guardians of our power grid. So the next time you look up at a power line, you won't just see wires anymore. You'll see a complex system at work, and you'll actually be able to spot the exact engineering solutions that are making it all possible. What other clever solutions are hiding right in front of us?